I want to say a great thank you to the organizers, to Gediminas, for this great conference and for putting Vilnius on the map of quantum physics. It's really nice. And it's a beautiful city, it's a beautiful place. And well, let me talk about my work or our work in Innsbruck. I need the pointer. Actually, the pointer doesn't work, we don't have laser pointers, but I will do it the standard way. So I'll talk about the topic you can read about there. Before I do so, let me quickly introduce the team, because certainly we do this work in a team, and I have a fabulous group of people, and I should in particular point to Sudipta, who did part of this work, Milena as PhD students, and E as a postdoc. And, but with great support from two postdocs or senior scientists, Manuele and Yang Liang. And I should say the work in my group wouldn't be possible without fabulous collaborators all over the place that you can read at the bottom. So let me directly go into the system, or actually first go an overview. I will rush you through this. We don't have much time, so I will rush you through various topics you will see later. So without further ado, without any big motivation, because we are all familiar with cold atoms and why we do this and why this is interesting and so on, let me actually introduce one of the platforms that we are using in my group. This is one-dimensional systems. And usually we add a twist to it, as you will see. But basically, in a nutshell, is we load cold atoms from a Bose-Einstein condensate into one-dimensional tubes. Ah, there is a mechanical. That's awesome. Awesome, awesome, awesome. This one is perfect. This is old school, yeah. Okay, very good. So we load into an area of tubes. Typically, we have 20 to 50 atoms per tube, transversely confined very strongly, and we have typically 4,000 of these tubes. So we don't look at individual tubes, individual realizations. Sometimes it would be good to be able to do so. The system is harmonically trapped along the this vertical direction very weakly. Also, that one would like to get rid of at some point. Certainly the system is inhomogeneous because initially the initial loading conditions are inhomogeneous. So I'll come back to that later. But it turns out this is a very rich platform for transport, localization, thermalization, and I will not even talk about everything that we can do with this. So one twist to add, as you will see, and that brings me to this workshop, Quasimodo, is to add spin impurity into the system. So spin impurity means just a different atom, basically an atom in a different state, but we don't do any coherent coupling, not in this talk. We're working on this right now to do other things, but this is just a different Zeeman sublevel. So the description of the system, as you all well know, is the Lieb-Lininger Hamiltonian. This is simple things you can write down. I mean, the crucial thing certainly is the interacting part, so we are really interested in strong interactions. I'll walk you through this a bit more in the next slides. We can tune in the not yet too strongly interacting limit, we can tune the interaction with the scattering length linearly, but it actually diverges at various points. Given by the confinement, interplay of confinement interactions, and that in fact sets an interactionless, an interaction parameter that's dimensionless. That's the Lieb-Lininger parameter involving this coupling constant and the 1D density. I'm sure you all know about this. This is standard textbook physics. The nice thing in the experiments that we can do nowadays, we can tune this Lieb-Lininger parameter through the interesting range around unity and a bit above, basically to as strong as quantum mechanics allows, and also, as you will see, we can make it negative. So this is a situation for the specific state of cesium. We have a zero crossing here. Here, for a few hundred Bohr radii for our density, we have a system that's already very strongly interacting around this range. We can climb up resonances and as you can already see here, we have a negative region, or on these resonances, we have a negative region. So this is well known. This leads to the regime of fermionization of bosons. So in a nutshell, and I'm sure you've seen that if you plot the correlation, the two-body correlation function, it would look like that for a weakly interacting gas. Well, at some point, certainly it has to tail off somewhere. And then the system, as you increase interaction, as the system fermionizes, it builds up these correlations. So basically what it means that the system is homogeneous, certainly, but this particle knows roughly where its neighbor is and so on. So it sort of wants to crystallize already. And in fact, that is this regime of supertongs, in fact, where it even does so, even more so. So, okay, so as you all know, 1D systems are special. This is the structure factor. This can nowadays be calculated for non-zero temperature also. This goes back quite some years by now. And as you see that this particle branch here, the Bogolyubov, the phonon branch actually goes then over into this more interesting spectrum with the LEAP 1 and LEAP 2 mode with this whole branch down here from the weakly interacting regime to the strongly interacting regime. So I haven't added anything yet. Now you can add certainly something. You can add a lattice to the system, which today I won't do, but you can add an impurity to the system. So again, there is this regime of negative interactions that we can also look at, and this is plotted now how, in a nutshell, for a two-body situation, the wave function would look like when the system starts to fermionize. So there's a sort of a kink, a notch in the wave function, and then the system becomes over-fermionized because we have, for strong interactions, the system has this second zero crossing here for the square of the wave function. This is known as the super-Tonge-Girardot gas, and I'm saying this already now because I will come back to that later. No impurity added yet to the system. Here is the specific form of how the coupling constant varies near this resonance. This quantity C is on the order of unity. It doesn't matter whether you put one, just put in one. So it's actually, the specific value then depends on your transversal confinement. So this is known as confinement-induced resonances, and on this one we actually switch into this. So interesting, the interesting regime is actually this and also this. Here you see here we go into this bound states down here when we go attractive near this resonance. Okay, I'll come back to that. So this we've looked at in my group for a long, long time. We've looked at so what do you see in this super-Tongs regime? It actually, the system becomes stiffer. So when you look at the breathing mode of the system, you see that the frequency becomes more than the value of 4 when you look at the frequency ratio between the compression mode and the dipole mode squared. That's long time ago. And in fact, only recently, I'm showing this now, I haven't shown the slide for many years because only recently we finally have gone back to the super-Tongs, and I'll show you why this is interesting. Okay, so what can you do with this Liebling-Linger Hamiltonian? How can you solve it? And there are various ways, and I'm not the expert certainly, we do the experiments. One version is to do beta-ansatz type. So basically a plane wave approximation with these momenta, which are known as rapidities here, called theta. And basically, this turns out for integrable systems, as many are probably even more experts than I. This actually can be used to solve the system and to even do dynamics. So this shows the characteristic behavior as the system fermionizes. Here, sort of shown schematically in real space. But basically, what we look up in our lab is not the real space distribution, but the momentum distribution. So in fact, in this fermionized regime, the momentum distribution is still Bose-like, right? It's peaked like this, yeah. So it still reflects the fact that it's bosons that want to condense at zero momentum, but the rapidities show this kind of very fermionic behavior, having this box-like behavior as you increase interactions. And these are actually accessible. And that's a nice example that also an experiment, as an experimentalist, one should read theory papers, but because we could have done these experiments that Dave Weiss did, published now 5-6 years ago, we could have done them in my group long time ago, but we were simply not smart enough. So basically the idea is very simple. You have the system described by these rapidities, you let the system expand in 1D, not in 3D, so you don't directly measure the momentum distribution, but you actually let it expand in 1D, and certainly there's one trick where when you want to do it exactly, you switch off interactions. And I didn't point to that, but we have the zero crossing, which whenever we measure anything, we always switch off interactions upon release. So you can then expand in 1D, and then at some point the system becomes really non-interacting, and then you can measure the three-dimensional distribution. So this is, in fact, this shows here with some simulations, GHD simulation, how that evolves as a function of time, and the theory actually is a very good match to our experiments. So we do this by adding a trap on top of the system Sorry, I forgot, for the rapidity measurements, we switch off interactions at this point. Not yet here. We let the system expand at the interacting system. So, okay, so what are the regimes? I told you about this Fermionized regime now. The rapidities are actually real numbers. But, and also there are real numbers for this excited state, the superton system. But it turns out they can, in principle, have they are complex numbers. What does that mean? Actually, it shows some decay, but that means that they are bound states. And actually, these bound states are known as beta strings. In the ideal case, you could actually turn your whole entire gas into one big cluster of particles. Question is it stable? What actually happens at short range? In short range, certainly these systems are not the one-dimensional at the length scale, let's say, of the van der Waals length. So that's evident, yeah. So these systems, this is certainly only, it does not capture the short-range physics, the short-range loss processes, molecule forming, and so on, certainly. Okay, anyways, so now before I come back to that, let me now add an impurity. And this is also theory proposal from a long time ago, and I'll show you also some old data. This is the dispersion relation of an impurity in such a strongly interacting gas, and you see this nice periodic behavior, and here already Dima Gangard and I say Kamenev suggested, well, what could be the problem with that system? How could it dephase or actually decay? Well, by emission of phonons, and certainly we hooked up and a long time ago already and said, let's look at the system. You'll see, so perhaps I say one more thing there. Oh, how do I go back? So the question is now, what do you do? The first thing you do is actually when you prepare everything at zero momentum, and then you would like to take the system onto this branch. The most simple thing is you just apply a force and you accelerate your impurity through the system, and that's actually then you will see will lead to Bloch oscillations. So it turns out that's very brutal, so we want to do something more gentle, and I'll show you the results, what you can do when you do it more gently. Okay, I have to tell you how this is in the experiment. This is a zoom in of what I showed you earlier, the scattering length as a function of magnetic field. Here's the 1-0 crossing I showed you, and this is now the interaction between the background gas, which is in this particular hyperfine state, and our impurity. So we do typically, as I said, 40 atoms or so, and on average one impurity. We don't do more than roughly one impurity. It turns out it doesn't matter so much for the experiments I'll show you in a second. So just for the experimentalists, when we are here at the 25 Gauss or so, we have already a strong, very strongly interacting background gas, and the interaction with the host gas is already very strong. Here, for example, we have a situation where the background gas already is, I would say, in this Fermionized regime, but actually the impurity doesn't see anything, just tunnels through the system. Okay, so these are, again, the interaction parameters. Now we have two, because we have, and it's both times set by the density of the background gas, because we have the two spin states. So, okay, now what we want to do is we want to sort of look at the situation where the background gas is strongly correlated and the impurity sees some finite, I is impurity, interaction with the background gas. And what you then expect if you were to put a force onto the system, that the system shows some Bloch oscillations. Whether you would see that is totally unclear. I mean, what's actually the characteristic length scale or wavelength of the system? Well, it's set by the density. So what you would expect is if you apply a force, given the density, you would then expect some repeated Bragg reflections on that background gas, on the two-body correlation function of the system. And this is sort of my comic now of what could happen then to that system. So we did this long time ago. Don't want to walk you through this. In essence, everything is here. We see this would be free fall, the dashed line, as a function of time. So this is mean momentum as a function of time. And we see this sort of damped wiggles. The green line is a no fit free, just a Benicio calculation, but not for an ensemble of systems, but for a single 1D system. This is the old data from years ago, more than by now, I think 10 years ago. And this is on the left side, this is theory. And then if you squint your eyes, you actually see these Bloch oscillations appearing. It turns out, this is for different interaction strength. It turns out we did a few things wrong at that time. Well, it was we knew about it. The force that we are applying is way too strong. That's why we create too many phonons in the system. So let's not be so brutal. Let's actually try to follow this branch adiabatically in some sense. And and not accelerate the system. So how do we do this? I won't walk you through the details, but in essence, we, on top of our magnetic forces, we add linear optical forces. So actually, we do optical levitation on the system, and with this, we can be much more gentle in the difference of the forces that is applied to the background gas and the impurity. So it turns out, this brings me to the first part now, I'm doing fine in time, I think, is actually that this realizes one-dimensional anions. So in a nutshell, you all know that if we exchange particles, we have a phase, and usually it's 0 or pi, but it could be something other, and this goes back to work by various people, in particular in Wandy, Haldane, Wilczek, and Martin Greiter some while ago. But there's been a long discussion since the 70s in Linus and Murheim whether there are particles with statistics between bosons and fermions, and in recent years, people have been, even in experiments, looking at two-dimensional anions, and there's a claim that one can even see the phase, the braiding of anions in such a setting. And there's the one is a Eintrap realization, the other one is done with superconducting processes down here. So anyway, so in our case, if we now follow this dispersion curve, it turns out that one can calculate the momentum distribution for this for the limit where the background gas is infinitely interacting, shown in this paper with beta ansatz in a strict way. So this is basically the situation initially. The black curve reflects what we've seen before, the narrow momentum distribution. There's actually some interesting behavior on the tails and so on, and it's not a delta function. But I don't want to talk about this. And then there is, it turns out that at the, I call this edge of the Brillouin zone here, at the blue point, the system becomes fermionic. Actually, when we dial in the momentum, that's then the Fermi momentum of the system given by the density, and the momentum distribution should then look like a box. And in between, you get a skew function, and that's actually then the anionic case, as we will see. So this summarizes what I've just said for the three example cases, extreme cases, and this case. So the question now is, can we see this in the experiment? And what's actually happening? So this is our comic now, only in a picture, but perhaps I directly go on the next slide then onto the math behind it. So basically, we have a very strongly interacting system of an impurity with our host gas, and that actually the strong interactions lead to spin charge separation. If we now give the impurity a momentum and we integrate out the spin sector, actually we get a system that is sort of dressed and looks like as it were behaved anionic. And that can be formalized here with in the operator language of a 1D system with this one spin. And after a generalized Jordan-Wigner transformation, actually you end up with operators that have this funny commutation relation, and it turns out that the phase is actually set by the momentum you dial in units of kf. So that's sort of the nutshell, and the question, is this all real? Can one do this? And in fact, we are certainly not the first ones to think about this. This goes back to various proposals that one could use impurities as probes for topological invariance and for interesting statistical physics, various groups. So it turns out when we measure the first order correlator, it's exactly on our system, it's exactly the correlator of these anionic operators. So in that we measure by Fourier transform, certainly we measure in this case I show you the momentum distribution. So, but you can do also other approaches. You can actually write down an anion Hubbard model in this way, as discussed today for the non-anionic case, but with this non-trivial commutation relation. So this is now the data already in our experiments as we vary the phase, or in our case the momentum, theory and experiment. We've developed with Nathan Goldman, we've developed yet another model, and you can actually directly also write down the full spinful Bose-Hubbard Hamiltonian without resorting to any anionic commutation relations and try to model the system. So what you see, if you squint your eyes a bit, from this narrow distribution, we get a skewed distribution, which then becomes sort of boxy. This would be the theory. Well, it's not perfect here. I think we understand why this is the case. So there are two things. It's not fully flat here, and it's certainly not also here, not totally boxy, but I think it's a good indicator that something interesting is happening. And certainly when you have this, you have to show that you can also screw this up, and I'll show this in a second. But actually we do understand why, for example, here the width is set by the fact that our Fermi momentum is actually not a single number, but it's a distribution because of the inhomogeneity of our system. And that actually carries through, so everything is convoluted with this kind of resolution, unfortunately. This could be done better if one were to be able to make one-dimensional box traps. So now, okay, perhaps quick. So one can now follow how this peak, this experimental peak now, walks through this Brion zone, let me call it this way, and how its population changes. And that is actually reflected in these two plots. The peak population, the peak location where it is as a function of this phase, and in momentum space, and the occupation, how much is in this peak. And all these models reasonably well agree with what we see in the experiment. Okay, so what I just mentioned, I actually skip this one. This is actually a release experiment. On top of that, actually we do two things to actually break this. And first of all, this shows if we increase the force, so basically in units of m times g, we are actually at 1/18, and this is our experimental data here at this value. And if you were to dial in a more brutal force, 1/3, actually that's the data that I showed you earlier, we were not able to do this optical levitation, you would actually see this kind of behavior, and that reflects the Bloch oscillation behavior. This is stronger forces, stronger forces, yes, or weaker forces, and this shows the system if you were to reduce or increase or reduce the interactions. So we did this in a rather strongly interacting regime. If you reduce interactions, the system actually loses this hunchback kind of behavior. And actually that brings me back to Quasimodo, because that's the hunchback, right? Anyways, so there are many questions on this about the dynamics of these systems. Can one do perhaps in space, different phases where the statistics changes? I think that's the most intriguing. So you have left, you have bosons, on right you have fermions, and what's the phase, the interface between the two systems? So I think that would be a fun question. Okay, so quickly on the beta strings. So because I introduced that, so what happens if you were to go into here? And in fact, so this kind of, I showed you this slide already, if you were to dial in attractive interactions. So what do we do in the experiment? So admittedly, we don't see these bound states directly. We cannot do spectroscopy on it yet. We cannot stabilize them yet. But what we can do is we can actually look at them in this kind of release measurements where we as I showed you before, where we measure the rapidities. And then look at how that compares with theory. In fact, those are the two things we can do. So theory is that here the solid lines, and dots are the experimental lines. So this actually shows the energy that we measure by these release experiments. So perhaps I was a bit too quick. So here actually we measure the release energy in 1D. I'll show you momentum pictures in a second. But we can also release in 3D. And in 3D, what we expect that in 3D actually release the binding energy of these bound states. And actually we see a huge difference in how when we release in 3D versus in 1D. And that's sort of one evidence that we have these kind of bound states then that we generate with a certain distribution in our system. And these are interaction ramps as we go over with a certain speed over the resonance into attractive interactions, and then look at our momentum distribution after usually in a time of flight experiment, certainly. Yeah. And The solid line is theory, and this, it's not under fit, it's actually fully determined by our initial conditions that we dial in with our distribution, atom number, average atom number, and so on. And it actually fits really nicely. Perhaps here there's a bit of a mismatch. So actually from these kind of calculations, Alvise, Bastianello, for example, can calculate the string population that we have at various temperatures in our system. So these are the typical temperatures are around a 10 nanokelvin, that where we start with. We can even go a bit lower, but we intentionally try to go higher to see that we create different distributions, and that's actually then reflected in the width of our sample after time of flight already in a very simple picture of like this. Okay, and let me skip this one. There's another evidence. So, lots of questions. So can one actually do more spectroscopy on these strings? And actually, at short range, the world is not one-dimensional anymore, and they should break up. Okay, I'm running a bit of time. I see the Sam and Channing, but let me actually give you give me 2 minutes on this. It's on the archive. I come back actually to the superton situation. So this I don't have to tell you, for bosons and fermions. So let me phrase it in the following way. If you have a system and you were to add a particle to the system, how many more states do you need? This is alpha. That's how I define alpha. For anyons, you need something between 0 and 1. For bosons, you don't need another state. For fermions, for each new particle, you need another state. The question is, can alpha be greater than 1? So some integer 2, 3, 4, 5, and so on. We would call them superfermions. Actually, the distribution would then look like this, where you have sort of holes in your distribution, but it's still boxy. What would be the indicator of that kind of distribution? If you Fourier transform it, if you know your sinc function from elementary optics, you would want to see wiggles. And in fact, how do we do this? How we actually dial in these zeros in a nutshell into this many-body wave function? Well, we actually cycle this constant, the interaction constant, schematically shown here, over one of these resonances. So basically going over the resonance once and twice and 3 times and so on, going through the tongs and supertongs and so on regime would dial in zeros into the wave function. In the experiment, this is how we do it. We ramp from some field onto the resonance to various, so already here we are strongly correlated, already fermionized. We go into even more fermionized situation, then jump across the resonance to the other side here where the system is attractive, and then ramp here through a zero crossing to D, and then go back and again do the same cycle. So this is, okay, more details I could provide perhaps later. And it turns out, just for the experts, it turns out that we do this within a few milliseconds, but system here at C, at this attractive regime, is amazingly stable. So over 1 second, we have perhaps at most 20% atom loss. Everything is done in 10 milliseconds. So this is the distribution, the momentum distribution of the system. Theory and a simple Thomas Fermi model, but let me show you, if you actually look at it more closely, as you will see the following, and this is shown on the left, the right and the left is the same. The left shows so the G1 function, and actually what's crucial is that you have these dips below 0. Here's the data, and on top of that is our essentially free parameter, no fits theory for the first cycle and for the second cycle. So the system becomes larger and the correlations die off quicker. That's the green curve. That's the second round. So just perhaps switch one slide, skip one slide. If you would, so this is actually when we go forward through this pumping cycle. This is the atom number. When we go back, in fact, we lose particles, and in fact, that's what brings me back to the beta states, because we actually have to go through the zero crossing, and we create beta states, and these are actually a lost channel. Perhaps one can do more clever by jumping these zero crossings. We haven't tried that yet. Okay, anyways, this summarizes this. So I think we can claim we have seen these higher order Fermi statistics. And I think it can be much done better. In fact, the theory is basically right on our experiment, and we know exactly what to do better when you have to do this in a homogeneous system. And because our temperatures are low enough, that's not the problem. Okay, and with this, I skip this part here. I guessed it already, how an impurity would move through a sample without dissipation.
This we leave for comments.
I leave for questions, yeah. Okay, thank you very much.
Okay, we don't have time for so we have time for a short question.
Tons of questions because there's tons of results. Congratulations. A quick one on the last part. You're saying, okay, well, if I have these super fermions, they require more than one state in energy space, so to speak, to add another particle. But can I really think of this as the ground state? Because in some sense...
No, it's not the ground state anymore. No, it's highly excited state.
Highly excited states.
Right.
But then, of course, also bosons or fermions will need more than one state if I have a lot of entropy per particle, right?
This is the last question I didn't get.
If I have a thermal state, then of course also bosons.
Yeah, you have to make sure that it's not a thermal state, right? But a thermal state wouldn't show a boxy distribution and would not show this kind of oscillatory behavior. That's the difference. That's our experimental
okay, so
it's
a non-thermal, but still
yeah,
state.
it turns out that for the higher state, because you're further out in momentum and energy, temperature doesn't play so much a role anymore. It actually gets better when you go to further excited state. You could ask, why don't we go yet another time? Well, then we pump so much energy in the system that the system is not one-dimensional anymore, actually.
Okay.
But it could be done. I'm sure somebody will get a good idea and do it better than what we've done.
Okay, I guess we have to move on. Thanks, Christoph, a lot. And